Okay, so now we're just going to do an example where we check. In fact, the most mysterious thing. Oh, we'll call it example 1. For chapter 16, we're just going to check that the time for an oscillation really is 2 pi square root. Oh, so I actually know what goes in there. My K, the units for K, are newtons per meter, right? Per meter stretched. And my units of mass are kilograms, of course. So, if I put in m over k, is that right? I'm pretty sure it is. Because if I have kilograms, and then remember how newtons was, so I have this meter that goes in the top, because it's newtons per meter, but meter was kilograms times meters per second squared. So everything cancels out except per second squared in the denominator. So that goes up to there. And I realize inside this square root sign I have per second squared. If it's m over k, it's not k over m. And remember, it was k over m for the frequency. So it's hard to tell just from memory which one it is. But if you check the units, then it works out. Okay, so we have a spring. You can draw it along with me. We're going to do this vertically so we can find out the spring constant. Okay, we're actually going to, let's mark it. Whoops. Y0. We're going to have, so you can't see me setting up. Try to fix that for next semester. Get to be able to see these setups. Okay. Near the top, we'll just set up a bar. Make sure my spring will stick to it. Okay, and I measured this is 0.5 kilograms, 5 newtons. Oh, need a meter stick. Oh no, and I forgot one, of course. Okay, on the homework you have a fun example with hanging a fish. So you get to answer your own problem. Like this, yep, a fish. So let's see. From the table below, the end of the hook is hanging at right about 60 centimeters, I think. Let's see how good that is. And that would be 0.6 meters. So then I put the 5 newtons on it, 0.5 kilograms. And now, the bottom of the hook, let's try that. Because is it the center of mass, or is it the bottom of the hook? It's 44. I think that will work. We'll see how many wrong turns I can take today. Okay. So I attach the mass, whoops, call that Y1. And this is 0.5 kilograms. So that tells me both the spring constant and the expected time period of my pendulum. Do you see that? So, if 5 newtons stretched the thing 0.6 meters, see that? 16 centimeters, 0.16, excuse me. 16 centimeters. Then, here, I have a spring constant of 5 over 0.16, 31 0.25 newtons per meter. Okay, so the formula predicts then that I should have to take 2 pi. Now why on earth is there a 2 pi? Times 0.5 divided by 31.25. Okay. So with this thing, if it oscillates, it should be 0.795 seconds per cycle. So let's get it oscillating, and this is a little bit tricky. I have to count, I'm going to try to count 5 cycles maybe between it reaching the top. So I'm going to pull it down and let it up. Okay, and then when it's at the top, 3, 2, 1, go. 1, 2, 3, 4, 5. Okay, I think that's reasonable. So what I got, you didn't want to time along with me? So what I got was 4.31 seconds over 5 cycles. Which is 0.862. Okay. Let's see. I think that checks out. We're like 10% off maybe. But you know, I'm just sitting here observing this with my eyes and stuff. So let's see, let's check real quick. If I had too much length here, my spring constant would be a little bit bigger, the denominator would be bigger, and the time would be even shorter. So okay, so I probably measured the height correctly, and my times are too long. Probably I'm just slow and I didn't anticipate properly, and I just recorded a little too much time. Right? It should have been really 4.0 seconds for 5 cycles, and I'm just slow by by 0.3 of a second. That sounds exactly like what a 40-year-old would do. Okay, but it's not off. Like I had to multiply by 2 pi. If I just did like without the 2 pi multiplier, it would be way too small. The pendulum knows 2 pi somehow. Oh, sorry. A pendulum is actually the same kind of thing, but the oscillator knows 2 pi. And what's even weirder, let's get it back to its equilibrium. And I'll give it less energy this time. I'll give it a little push. Should we time 5 cycles of that tiny little one? So let's see. 3, 2, 1. 1, 2, 3, 4, 5. 4.37 again. I'm just as slow. Maybe see, that makes, it's usually really perfect. So we're probably like off for some reason. Maybe the spring was actually, maybe this is shorter. So the spring constant should be, oh, no, that's it. The spring constant is probably actually a little less than it is, which would make this time longer if the denominator is smaller. So I should have measured more distance, not less. So I probably should have measured to the center of mass, from the tip of the spring to the center of mass. Okay. Oh well, we still got really close. By the way, so I did need to say that. A pendulum is another common oscillator. On the very first day, I didn't want to get into this so much. How do we derive these formulas? There are some fancy physics derivations. We're not just guessing. But for today, it's a Monday. A pendulum does the same thing. It also oscillates. But its time is 2 pi times the square root of L, the length of the pendulum, divided by G, you guessed it, gravity. Instead of a spring, so K is in the denominator for the oscillator, the spring force restoring the oscillator. Well, with a pendulum that's just swinging back and forth, look, I can kind of turn this into a pendulum. Oh, no, it does both. That's terrible. Anyway, a pendulum that just swings back and forth like a kid on a swing, it just depends on the length of the swing and good old G for gravity. 10's close enough. Did you ever notice on the playground the longer swings go slower no matter what you do? You can make them bigger, right? But the kids on the longer swing get behind, and the kids on the shorter swing always do a shorter back and forth. You can go faster, but you just travel the distance, travel a longer distance at a greater speed, and you end up at the same time. We'll work that out with math in the rest of the week. You don't really need to have worked that out to answer the questions. Okay. Any questions now? No? All right. Give it a try. Oh, let's leave that there. If you're still giving effort at the end of the week, then I'll just release the answer key before it's due.